Yes, hello everybody. In last class, I have discussed about the Coulomb's force, electrostatic force, the nature, the theoretical analysis of electrostatic forces, and electric charge. What is actually our electric charge? Today, I am going to discuss about problems based on Coulomb's force or electrostatic force. How we solve the numericals, how we deal the problems based on these three things. So this is the beginning of the electrostatic numerical section now. See, while solving electrostatic force or Coulomb's force, we meet with the first type of numericals that are equilibrium points. Equilibrium points mean the points where any third charge can feel no force. So I'm going to analyze that. See. Suppose I'm taking a plus q here and a plus q here. These both charges are equal in magnitude and there is some separation in between them. That is R. So can you tell me that where should I put a third charge, whatever be its magnitude, so that it feels zero force? Means suppose I have selected 2 points. One is in between them and 1 point is out of them. See, suppose I put a test charge here on Q. Is it visible clearly? Suppose I am putting a test charge here at point A. Then what would happen to point Q0? Will it experience any force here or will not? If I put a test charge Q0 here on B, will it experience any force, electrostatic force or Coulomb's force here or not? Let's check here. See, at this point, the force by this plus Q to Q0 is repulsive, and actually it is in this direction. And force by this Q is in this direction. So these two forces are repulsive. So to cancel the resultant force on Q0 here, we need to equal these two forces and have these two forces are equal only when this point is at the midpoint. So this point will be the midpoint. Only then the forces will cancel. Understood? So here we are getting that the force experienced by Q0 at point A, which is the midpoint between plus Q and another plus Q, will experience zero electrostatic force or zero Coulomb force. We call it an equilibrium point. So A is an equilibrium point. Second, let's check what happens at B. See, if I put a test charge Q0 at B, so force by this plus Q is in this direction. And force by this plus Q is also in this direction. But here, the distances between these two charges and these two charges are different. Rest all other things are same. So the magnitude of forces experienced by Q0 at point B is not equal in magnitude. So these two forces are not equal in magnitude and they are neither opposite in direction. So they will not cancel each other. And so you cannot say, you can say that B is not an equilibrium point because Q0 is facing zero force here. If Q0 will face zero force here, it means that B is also an equilibrium point. But you are seeing that we are not getting any points out of the periphery of these two charges as an equilibrium point. So the same condition appears here. If I put any point here, here or here, that is also not an equilibrium point. So you just get equilibrium points in between them. When the charges are equal in magnitude, then you get an equilibrium point exactly at the midpoint of the charges. So B is not our equilibrium point. Similarly, take a point C here, Q0. C is also not an equilibrium point. So it's clear. Now come unequal charges. when I'm going, let's see this. What happened? Is it any messages?
Yeah,
Okay. So camera is on or not?
it's already on.
It's already on. See, if I'm changing the magnitudes here, see, let's make some changing in the same figure. And in that case, yes, just normally the distance between them is r, as we have done in previous question. See, this time the sign of these two charges are same, but they are not equal in magnitude. This time one is q1 and another is q2. Give me this, don't take this. Magnitude is q2. So these are different in their magnitude. Now I can take the 3 points. Take a point A somewhere in between Q1 and Q2. At a distance x from Q1, take this point A, a point B, and similarly a point C. So first do some qualitative analysis to find the equilibrium points. C, put a test charge at C. So the force by Q1 on this charge is in this direction, that is F1, FC1. Means force over charge Q0 at C by charge Q1. Now check the force of Q2 on this Q0. It's also in this direction because they both are positive in charge. So FC2, and as this distance is lesser than this distance, you can think that the two forces on the charge Q0 at point C by Q1 or Q2 may be equal or may not be equal, but they never cancel each other because why? The directions are same. So this point is not an equilibrium point. So we conclude that C is not an equilibrium point. So if you select any point from Q0 to this side up to infinity, you don't get anywhere an equilibrium point. Similarly, make the same analysis here on B. Force by Q2 is also in this FB2. Put a test charge here, and force by Q1 on B. So see, similarly the analysis we have done here at point C, we'll have to do the same analysis at that point B. Force by Q1 on point B, a test charge is kept at this point Q0. Force by Q1 on this Q0 is FB1, is in that direction because this is positive. Force by Q2 on this Q0 is also in that direction because this is also positive, and that is FB2. Again, the distance here and here are different. So we may have equal force FB2, FB1, or may not in magnitude, but in direction they are not opposing to each other. So there is no any chance to cancel each other, and that's why it's also not an equilibrium point. So B is also not an equilibrium point. So if you take any point from Q2 to infinity, like B, here, there is no chance of getting an equilibrium point to that side of Q2 and to this side of Q2. Now, the reason left is only this. So our guess will be that only this reason gives us an equilibrium point in between. So in previous case, suppose at point A, do some qualitative analysis now. Put the test charge at point Q0, A. Force by Q1 over Q0 is positive, so it will be in this direction, FA1. Similarly, Q2 also applies force on Q0 at point A, and that will be in this direction, that is FA2. And these two forces are in opposite directions, so there's probability that they will cancel each other if they have equal magnitude. So the charge is different and the distance are different. So there is a probability that they may be equal or may not. So let's check that. So according to our analysis that we must have equilibrium points in between, and we let a point A to be equilibrium points. It means that the forces appearing on Q0 by Q1 and Q2 are equal in magnitude but opposite in nature, and so I'll have to check that. This distance is R minus X. So for A to be equilibrium points, FA2 must be equals to FA1, or that will be this 1 by 4 pi epsilon naught Q1 Q0 by x squared is equals to 1 by 4 pi epsilon naught Q2 Q0 by R minus x squared. Q0 cancel, this total cancel. So what are you getting now? R minus x by x whole square is equals to Q2 by Q1. And finally, R minus x by x is equals to under root Q2 by Q1. So this is our relation, and by solving this equation we can get the value of x easily. Means we can predict the equilibrium points at A, which is at a distance x from Q1 and at a distance R minus x from Q2. So from here, notice here, what the ratio tells us. Ratio tells us that if the charge is heavier in magnitude than this charge, then this equilibrium point sits towards the Q1. So it will be closer from Q1 and it will be farther from Q2. Similarly, if the Q2 will be heavier in magnitude than Q1, then this point sits closer to Q2 than Q1. And the condition here, if Q2 equals to Q1, in that case, x will be R by 2. So if Q1 is equals to Q2, you get A exactly at the middle point that we have discussed earlier. So for the positive charges, we learned here that the equilibrium points are only in between the charges, neither this side to the charge, neither this side to the charge. So only this reason gives us equilibrium point in case when both the charges are positive. And you can notice here that this equilibrium point is free with the charge. So the whatever charge I place here, it must be in equilibrium. But notice one thing here. So I'm going to raise this exactly. So if Q1 is equals to Q2, x is equals to R by 2. One note. Second thing, equilibrium point is free of magnitude of charge over it. But if this charge is quite heavier than this two charge, then our whole concept will be in vain. Because why? If the charge here is very, very larger than this Q1 and Q2, then it will attract Q1 towards itself or attract Q2 towards itself, or it will repel Q2 and Q1 to a large extent. Then our setup will be destroyed. So the point is free with the magnitude of charge Q0 here, but it should not be much greater than Q1 and Q2. So we learned how to find equilibrium point when both the charges are positive, they are equal in magnitude, either they aren't equal, but we can find easily what is the equilibrium point in between them. Now do a simple analysis here again, learn something more. What happens if my test charge will be negative in the case here? then I need to remove all the setups here. Suppose I know that test charge is not a negative charge, but if I take some very small negative charge here, so can it justify my equilibrium points as Q0 has justified? Let's see, again take the 3 points. The calculation will be same, but here we can justify it just doing qualitative analysis, no need of quantitative analysis, because why? To find the distance x, we'll have to go through the same procedure, and in that case, this Q0 has no meaning in the calculation. Take a point B here. So, Q0 here too, and minus Q0 here too. Let's check here. First, come to check on this point. Force by Q1 on this Q0 is attractive, it is in this direction, that will be FB1. Because Q1 pulls Q0 towards itself. So the force over Q0 by this Q1 is in this direction. Force by Q2 on Q0, actually it is minus Q0, so it also attracts minus Q0. So this force is also in this direction. So again, both the forces are in same direction. They may be equal in nature, in magnitude, or may not, but they are in the same direction, so no probability of getting any equilibrium point here. So B is not an equilibrium point. Is it visible?
Yeah.
So B is not an equilibrium point. Let's check C. You can check it by simply making the analysis. From Q0, again it's negative, so Q0 pulls it towards itself. So this force is FC1. And Q2 also pulls Q0 towards itself. So this is also in this direction. And that will be C2. And both these forces are in the same direction, so no probability of getting an equilibrium point at C. So again, C is not an equilibrium point. So again, we come to the conclusion that when the charges are same in nature, whatever be their magnitude, we don't get equilibrium points to the sides of the charges. We get equilibrium points in between them. So go through it. Now make a qualitative analysis that minus Q0 is supporting the equilibrium point at A or not. Let's check it. Force by Q1 over minus Q0 is attractive at this point, and this direction is FA1. Means force over minus Q0 by Q1 is attractive, so it is towards this side. Similarly, force by Q2 over Q0 is in this direction, it's attractive, so FA2. And as we see here, these two forces are opposite in nature and having different magnitudes of distances and charges. The probability that they will produce an equilibrium point is quite high. So we reach to the same conclusion that whenever the charges are n charges are equal in this sign, either positive or either negative, then we must get an equilibrium point in between them, not to the side of Q2, not to the side of Q1. So A is equilibrium points. Equilibrium point. There's a question arising inside your mind. Can I make minus Q1 and minus Q2? Then can I get the same analysis? Yes, exactly. These two charges have equal sign. Then you must get equilibrium point in between them. Not to that side of charge, not to this side of charge. Okay? So I think I have learned one part of equilibrium points. Now I'm going to learn when we have different charges. Means Q1 and Q2 are different in sign. One is plus and one is minus. Then wherever I get the equilibrium point. So I'm erasing this. If this will be the case, still a point in between them is an equilibrium point. No equilibrium point towards here, infinity to this side. This goes to infinity. No equilibrium point. No equilibrium point to this side. So again, the same analysis. If the charges are same in sign, they are both negative here. So we don't get any equilibrium points to this side of charge, to that side of charge. Just we get equilibrium points in between. Means you have to notice that whenever the n charges have the same type of charge, they are either positive or either negative. In that case, you must get equilibrium points in between them. Not to that side of charge, not to that side of charge. But as I told you that I'm going to discuss here right now that what happens if my one charge is positive here and another charge is negative here. What happens? One charge is positive here and the charge is negative here. So in that case, first make what happens. It's not visible.
Yeah, it's visible, but more with a little bit. Yeah, speak now.
What are you doing?
I'm pushing something inwards.
Tell me, I'm going to do this.
Yeah, leave it.
So what's the situation now? Is it clear?
It is clear. It has a little problem.
What?
It's trying to adjust.
What's trying to adjust?
See, it's doing it by itself. The phone.
So it's going on. Okay, let it to go.
Let it to go.
So see here. Let's talk the recurring ones.